Okay, thank you very much, Yenrong. I'm so sorry I couldn't come in person, but thanks a lot, organizers, for allowing me to give a Zoom talk. So this will be partially the review talk on this topic of the negative geometry expansion, but I try to highlight the results of a new paper, which is now done. We are just doing proofreading with Lance Dixon, my student Umut, with Shruti, who's a postdoc at Brown, Yongquin, who's a student in China, and Sean, who's a postdoc in Munich and will soon move to Penn State. Okay, so the topic of the talk will be amplitudes in planar n equals 4 super young mills as a playground for theoretical ideas, both in mathematics and physics. And we will use many of the ingredients here on the list and many of the recent developments in this talk and try to connect them through these negative geometry expansion. So the topic or one object we will be interested in is the loop integrand for scattering amplitudes in this theory as a rational function of many variables, not only the external kinematics, but also the loop variables. And on this side of the story, this rational function can be interpreted as a canonical form on some positive geometry called Amplituhedron. It's not strictly positive geometry. There are some caveats, but it's kind of positive adjacent geometry. And this is something which is understood. The geometry is understood, the definition of the form, the way how to calculate the form in general is not understood. That's a difficult task. Now, the physics tells us that eventually we should take this canonical form, this integrand, and integrate it over a certain domain. In physics, this domain makes perfect sense. It's the real Minkowski contour. What this domain really means in this geometric picture of Amplituhedron is still kind of unclear because the domain in which the Amplituhedron is defined is not the domain we are integrating over. So it's a different element that we have to bring from outside, from physics. And then if we do this integral, we get a loop amplitude. And this is now just a function of kinematical variables because the loop variables are integrated over. But it's a very complicated function, transcendental. In this talk, we will mostly talk about polylogs, but there are even more functions, elliptic functions, and we don't even know the function space. Even at relatively low loop order, we don't know what exactly can show up in amplitudes. Now, there is a reduction of this information of the amplitude to the symbols, which is some combinatorial data which encode branch cut structures. And there is a close relation to a different type of mathematics to cluster algebras. This is something I will not discuss in details, but we will use the symbols and we'll show a lot of symbols at the end of the talk. And the point would be to relate the properties of the integrand and the amplituhedron geometry to what we see in these transcendental functions and also in the symbol. Now, in fact, my picture was a little bit simplified, but because if we literally do this integral over the Minkowski space, we get infinity. There are divergences. And the standard approach to regulate it is using dimensional regularization. But this actually doesn't play very nicely with geometry. The definition of this amplituhedron geometry really relies on the fact that we live in 4 dimensions, not 4 plus 2 epsilon. And but we still want to go to the other side. We still want to do the integral and study these functions. So motivated by some physics intuition, BDS ansatz, and the way how the IR divergences look like in this theory, we can define some close cousin of amplitude, which through some operation, which gives actually a finite result. Yeah. So the object we will actually consider will be not the amplitude itself, but the logarithm of the amplitude. And that object will give us this sum over negative geometry. So instead of having the amplitude, the integrand of the amplitude as one amplituhedron, we will have the logarithm of the amplitude as sum of amplituhedron-like objects, which we will call negative geometries. Now, the motivation to study that is twofold. So in mathematics, we just would like to learn some lessons and get some intuition how to calculate canonical forms from complicated positive geometries and beyond, uh, to develop some techniques, and also use some knowledge and special properties of the amplitude from physics. And even now, it's not immediately clear how the properties that we see in physics and use to write down the form, to determine the form, what actually does it mean in math? I will see some examples. Yeah, we know that something must be true in physics. We can inject this information when we calculate a form, but it's not totally obvious from the definition of the positive geometry what this property is or how it should be used on that side. And then we would like to link these special properties of the integrand to patterns in the polylogs and the symbol. On the physics side, these negative geometries will give us some nice building blocks for amplitudes, motivated by the amplituhedron, but maybe we can even think about them independently as some nice integrals. And they will allow us to produce some higher loop data that we can then study. Yeah, eventually you will see that we will be not able to calculate a full amplitude, but we will be able to go to high loops, in some cases infinite number of loops with these building blocks. So calculates individual building blocks. And then more ambitious motivation is to find some exact expressions in coupling. So sum over or loop orders, not necessarily for the amplitude that we will be not allowed to do, but potentially we would like to do it, and study the function as a function of coupling, not just as a function of kinematics. So here in this formula, the f will be the function we will eventually study. It will be like the amplitude, but it will only depend on one kinematical variable. That will be a huge simplification. And it will also depend on coupling. And while we have a lot of access to the weak coupling expansion using different methods, there also exists some results at strong coupling, but how to connect them together is, of course, an extremely difficult and important question. So we will show in very, very tiny examples how to do certain resummation, some approximation, when we single out only certain negative geometry and we resum them and then study the behavior at strong coupling. Okay, so now let's first discuss the loop integrands. So the standard methods to calculate loop integrands, method of Feynman diagrams, but in our context, we will also use the unitarity methods, or we take it as a standard method from our point of view. And this is expressing the amplitude, the integrated amplitude, as a sum of integrands I, which are integrated, and with some kinematical coefficients. And this I is some basis of integrals. They are theory dependent. Depending in which theory you are, you need different bases, bigger and bigger, if you are in more and more complicated theory. This is an example of some free loop amplitude in n equals 4 super Young-Mills, so the theory we will be interested in. The integrand is always some numerator over denominator. The denominator is something trivial we can immediately read off from the sequence of Feynman propagators, and the numerator is something non-trivial that we can choose, and some numerators are better than the others. Now, the coefficients, these C coefficients are kinematical coefficients, which in the context of unitarity methods, we then fix by the method of cuts. So they become products of three-level amplitudes, something that we input from the theory, from physics. Now, in planar n equals 4 super Young-Mills, there is a long history of calculating these integrands, especially for 4-point. So for the simplest 2-to-2 scattering, and this is something I will now quickly review because that will be also eventually the object we will be mostly interested in. So the 4-point amplitude actually played a crucial role in so-called BDS ansatz. So in 2005, Bernd Dixon and Smirnov calculated the free loop amplitude 222 in 3 loop 4-point amplitude in this theory, based already following up on the results of 1 loop from 1982 and 2 loop from 1997. And they integrated, so this is the integrand, and they integrated the result in dimensional regularization, and they found that there is some surprising iterative structure. Looking at it more closely, they conjectured that the amplitude, they conjecture it for n point, but we know now that it only applies for 4 and 5, and starting at 6, there is some extra remainder. But at the time, they conjectured that the full amplitude exponentiates basically from the 1 loop amplitude. And there are also some numerical coefficients which also depend on the epsilon, on the dimensional regularization parameter. But more or less that the amplitude exponentiates, up to some numbers which are in general unknown. But one of the important number was known in this BDS formula, and that was the cusp anomalous dimension, which controls the leading IR divergence in this theory. I will talk more about that later. It will also play an important role in this talk. So this was at free loop. This was conjectured based on the free loop result. And in the next couple of years, the 4-loop integrand and 5-loop integrand were constructed. In the meantime, the dual conformal invariance was discovered in this theory. So these numerators are now typically chosen to be dual conformal invariant. And this cannot be really integrated. The technology is not there to do the full integrals. So at this point, it was a construction of the integrand. Some of the 4-loop result was integrated, and the conjecture with the leading IR divergence being cusp anomalous dimension was confirmed. Now, today we have data actually for this object, for the integrand, up to 12 loops. There are some interesting integrand method to calculate 6 and 7, and then eventually using the duality with the correlator and F-graphs, it was possible to go up to 12 loops in the paper by Jake, Paul Heslop, Song Hee, and other people. So this is basically the frontier of the perturbation theory calculation. There are data to 12 loops. Of course, they are massive. There is a huge number. Even these extremely compressed F-graphs, there is a huge number. But these data are available if necessary. Okay, I would like to just mention that we will here follow the link of integrand, integrate integrand, and get the finite answer. But there are also other methods which totally bypass the integrand part, and directly looking at the symbol and bootstrapping symbol, something I will not talk about, but there is a huge number of people worked on this very successful approach and produce very high loop order data, even for higher points, per 6, 7, and more. Okay, but now we will focus on the integrand, and now from a point of view of being a single rational function. So even in these unitarity methods, when I wrote this, these integrands for individual diagrams were really supposed to be integrated and not summed up. But for planar n equals 4, or in general in planar theories, there is a reason why to flip the integration sign and the summation and talk about a single rational function that needs to be integrated afterwards. And in the context of planar n equals 4, this makes even bigger sense because it enjoys the dual conformal symmetry. There is a connection to the positive Grassmannian. This function can be not only written using some integrals, but also recursed using recursion relations. So this is an extremely nice function, and this is the thing which has the interpretation as the canonical form on the Amplituhedron. So the loop integrand, which depends, written in the momentum twister space, depends on some external momentum twisters, and then also on lines which represent loop momenta. Okay, but this brings us to the Amplituhedron, and this starts with the definition of the positive geometry, which actually came partially as a consequence of the existence of the Amplituhedron, but it's much more general. And this is just a physics layman definition of the positive geometry. So we have some space of dimension d given by some polynomial inequalities. We map the kinematics from our amplitudes to some parameters xi, and then we chop out the space by polynomial inequalities in these parameters. And then the space is equipped with a differential form omega with logarithmic singularities on the boundaries. So whenever we tune the parameters to go to the boundary of the space, we generate a singularity dx over x and the differential form on the boundary, which has one lower dimensionality. So there is a simple example just of a 1D geometry, which is a line segment. This is chop out by two linear inequalities, and the canonical form looks like that. So the Amplituhedron is built on this idea, and it's just much higher dimensional, and the inequalities are not linear but polynomial. But in principle, it's the same idea of mapping the kinematics into parameters and write down the inequalities and define the differential form, and the differential form will play a role of the loop integrand. So the Amplituhedron is labeled, the geometry is labeled by four parameters, n, k, l, and m, which now play a role in these inequalities, but in physics, they stand for the number of external x, n, k is the helicity number. For k equals 0, we get MHV amplitudes. In the gluon sector, 2 minuses and the rest plus, and then for more minuses for other sectors, the k is higher. L will be the number of loops, and m is some additional kinematical parameter which has no analog in physics. So in physics, it is set m equals 4. And our focus in this parametric space will be for n equals 4 point, k equals 0, MHV. At 4 point, there is only MHV, so only k equals 0 is possible, and m equals 4. So we would call it MHV 4-point amplitudes to all loop orders, because we allow L to vary from 1 to infinity. And the loop integrand, the 4-point L loop integrand, is then encoded as a canonical form on this Amplituhedron space. And because this is it's much simpler space than the general Amplituhedron, because we already did all these restrictions. So the external momenta are given only by four momentum twisters Zi, and inequality tells us that the 4x4 determinants of these Z's, which are points in projective space P3, they are 4-component projective vectors. The 4x4 determinant must be positive. And the loop momenta are represented by lines in this space, which we typically denote AB with two arbitrary points A and B on a line. And the Amplituhedron conditions are just these 6 conditions. Again, on the 4 brackets, on the 4x4 determinants, which link the AB to the external momentum twisters. In fact, in this simple example, these inequalities just boil down to the inequalities in the positive Grassmannian G plus 2, 4. However, this is just for one loop. If we have multiple loops, we have to impose these inequalities for each of the loop. And then all the non-trivial part of the Amplituhedron comes from additional quadratic inequalities, bilinear in each in individual loop lines. And that means that the 4x4 determinants given by the two of the loop lines, ABI and ABJ, must be also positive. So we just stuck these two positive Grassmannians G24 in a big 4x4 matrix and impose that this matrix has a positive determinant. Now, exactly, it's these quadratic inequalities which make everything rich and complicated. And this is also the reason why the Amplituhedron beyond one loop is not a positive geometry, and was studied these because of the presence of some internal boundaries studied by Paul and Gabriel several years ago. Now, in parametrization, if we take the line AB, we can parameterize it. We can expand the points AB in terms of the external momentum twistors. So this is just a parametrization of the line. This is representation of the G plus 2 4 matrix. And for this parametrization, the inequalities boil down to very simple statement that all these parameters are positive. So once we have that, the canonical form, it's just a very simple D-log form in all these parameters. And then we can reverse it back and write the canonical form back in terms of these minors. And then, as we will see later, we can also write it, of course, in terms of these 4 brackets, which is what we will eventually would like to do. Now, if we have L lines, then in addition, each line is then parameterized by 4 parameters. In addition to these 4 parameters for each line being positive, there are these quadratic inequalities, which have this form in terms of the parameters. And we have a lot of them because we have L choose 2 at L loops between any 2 pairs. And it is a difficult now question to take these inequalities, even in these particular parameters, which seem to be very convenient for this problem, and triangulate the space and find, in terms of some simpler geometries, some analogs of simplices, and for which the canonical form would be trivial, and then sum over all of them. So this is still very hard to do in general, and it was explicitly done only up to 3 loops. Now, from physics, we actually do know that there is a triangulation of this space provided by the BCFW recursion relation. It's just that naively it doesn't look supernatural in terms of these parameters, because the loop BCFW relates the L loop MHV amplitude to L minus 1 loop NMHV amplitude, and then the K grows and the number of legs grows if you continue the recursion. So naively the space looks very different, but it was recently shown and by Pasha Galashin that the recursion relations indeed triangulate the amplituhedron in some more natural way, and for demonstrating that he used some interesting origami patterns. His paper is still not yet out, but there is already a Quantum magazine article about it. And yeah, this might provide a clue how the triangulation works, in particular in this context of the BCFW recursion relation. Okay, but however we triangulate it, in the end, the canonical form has following structure. So there is some denominator given by the product of propagators, which we know in advance because these are just Feynman propagators. They correspond to the first boundaries of the amplituhedron. So these are the objects that have definite signs that we put inequalities in. So we can always write the denominator directly without any work. But then all the non-trivial work is in determining the numerator of the form. And the numerator does a lot of interesting things. It vanishes at certain points, and it has a lot of properties and must satisfy a lot of conditions. In addition, the form being projective in all variables, this restricts the numerator already, but not enough. The numerator has also ensured that the form is logarithmic. Naively, if we just put 1 in the numerator, then starting at I think 5 loops, we would start to get double poles in the denominator, or even 4 loops, I think. So the numerator must cancel these double poles and preserve the logarithmicity of the form. But the numerator must do much more. It must make sure that the only singularities, not only the first singularities, but all higher singularities that the denominator produce and do survive are the ones which are allowed by the amplituhedron inequalities. In fact, in physics, we would say they are allowed cuts. The numerator must cancel all the cuts which are not allowed. Okay, So now let's transition to these negative geometries. So here we ended with the amplituhedron, some geometric space, canonical form. The canonical form reproduces the loop integrand. The form has this structure. The cuts of the integrand corresponds to taking residues of the form, which corresponds to going to the boundaries of the amplituhedron and evaluating the form on these boundaries. Are there any questions here before we proceed? So let's now move to the negative geometry. So we have to first look more closely at these IR divergences of amplitudes to get the motivation to what we are going to do next. So amplitudes in gauge theories and n equals 4 superyoung specifically 2 are IR divergence in d equals 4. If we use dimensional regularization, so we move from 4 dimension to 4 minus 2 epsilon, the amplitude becomes a series in 1 over epsilon, where at L loops the leading piece is 1 over epsilon to 2L. Now, the IR divergency in fact exponentiates, so most of these higher orders are just come from iteration of the lower loop data, and the real new divergence only sits at the 1 over epsilon square level. And the coefficient of that is a function of coupling. If we now consider a resummed object, when we dress each L loop amplitude with some power of the coupling and sum over all loop orders, in n equals 4 super-Yang-Mills, these coupling constants don't run, so these are only numbers really, so we can really just dress it and sum it. So then it exponentiates, and the coefficient of this leading 1 over epsilon square divergence is called cusp anomalous dimension. This also suggests we should take a logarithm of this object, because the logarithm of this object is directly only 1 over epsilon square divergent. So this is also why we will use the logarithm just in a second, because this is a very mildly IR divergent object, and using some very simple operation, we will make it IR finite. So this is also the reason to take the logarithm seriously. But this is for the integrated amplitude in already regulated in dimensional regularization. So let's now think about, can we construct an integrand for the logarithm of the amplitude prior to integration? Okay. If we take the logarithm of the amplitude, we can express in coupling, and then if we express the amplitude in the coupling, if we take the logarithm, we can now do the series expansion, the Taylor expansion in G, and just combine individual terms at a given order in the coupling. At one loop, we just get a one loop amplitude, but at two loop, we get a combination of two loop amplitude and one loop square. At three loop, we get a combination of three loop, two loop, one product of two loop, one loop, and one loop cube. And while each of this term has maximal divergence, for example, at two loop, it's 1 over epsilon to the 4, this combination is only 1 over epsilon square divergent. So this is a motivation to consider the logarithm of the amplitude at the integrand of the logarithm, because we can just take this combination of two loop objects, which for 4-point amplitudes in n equals 4 are just two double box integrals if we write it in this representation, and one loop is given by single box integral. So we can take this combination, and this is our integrand for the logarithm. Now, one thing I forgot to mention, so let me just go one slide back, is that this cusp anomalous dimension, which will play a very important role at the end of the talk, is actually known exactly in this theory from integrability, or at least conjectured to be known. There is an explicit formula of this object, gamma cusp, as a function of coupling. At each order, if we expand at small g, at each order, we get a number this number is a combination of single zeta values and very low loop order. These are just powers of pi, but here we already can see that this is a combination of pi to the 6 and zeta 3 square, and then it continues. But the only objects which can appear at weak coupling are products of these single zeta values, which are these sums, and they are also polylogarithms evaluated at special points. There is also an expansion at strong coupling, but at strong coupling, it doesn't exhibit this uniform transcendentality behavior. Now, this is where the integrability of n equals 4 from this Beisert-Eden-Staudacher equation kind of enters the amplitudes, because they predicted this function to any values of coupling, and this seems to play a role as the leading IR divergence of the amplitudes in this theory. Okay, so we will get back to because this will be the final thing we would like to calculate using these negative geometries and do some comparisons. So let's go back to the amplitude logarithm. So we defined here an integrand as combination of integrands for the amplitudes. Here we are critically using the fact that we are in planar theory. So we have a planar integrand. So it makes sense to combine these objects together. They are just rational functions of the loop lines in the momentum twistor space. And these are global variables. We can define them for any amplitude. Products of amplitudes are also fine. These are not necessarily planar. We wouldn't call it planar because this is not one Feynman diagram, but rather the product of Feynman diagrams. But we can define this loop integrand, and this will actually have a geometric interpretation in terms of these negative geometries. So this is where they actually enter the story. But for that, we have to start with the amplituhedron first and do some graphical operation. So this picture now represents our amplituhedron space. Each dot is one of the loop line. So this is a 5-loop object. And each dashed line represents an quadratic inequality between the two lines. And each of the one-loop line lives already in the one-loop amplituhedron, satisfies these simple linear inequalities, but the dashed line stands for the quadratic inequality. So this is how we would graphically denote the 5-loop amplituhedron. Now, the quadratic inequality says that the 4 bracket of the lines which connected by this edge in the graph is positive. So the other option then being positive is also being negative. So we would denote this option with a solid red line. And if we take the union of these spaces, then there is no condition because it can be both positive or negative. So using just this simple replacement, we can replace all the dashed lines for the positive inequality, which represent the positive inequalities, in terms of the solid lines representing the negative inequalities. So in terms of, instead of one diagram, one geometry, we get a sum of many geometries. And here we should think about the picture being the canonical form on the geometry. So we got a sum of many with some signs. Each link is this negative inequality. Now, obviously, if we have a fewer of the links, this would be a simpler geometry. In particular, if there are no links at all, which is also a part of this sum, this is a very simple geometry of 5 lines which just don't interact with each other. There is no single quadratic inequality. And the canonical form for that should be just the canonical form for the one loop 4-point amplituhedron to the 5th, or the 5 copies of the same thing. Now we can restrict the sum to the connected graphs only. This has also in the sum disconnected graphs. If we restrict ourselves to the connected graphs, we exactly get this integrand for the logarithm of the amplitude. So this is the restriction we will do now. And the logarithm of the amplitude, the object that will eventually integrate to the logarithm of the amplitude and will be very mildly IR divergent, as we saw here, is given by the sum of the canonical forms for these, which we now call negative geometries. So this is a bit bad name because this is still a positive geometry in the same sense as the amplituhedron, but the links here are negative inequalities instead of positive inequalities. So that's the only difference. And also the sum here involves the geometries which have any number of links as long as the graph is connected. The amplituhedron was only a single geometry where was a complete graph, where all the links were present. So here there is hierarchy, which will be important just in a second, when some graphs have smaller number of links, some graphs have bigger number of links, and there is a graph which has all links. And this will be as complicated as the amplituhedron itself, and the integrand will be as complicated as the integrand for the amplitude. But there are these simpler objects as well in the sum. Now, know that each term is a canonical form on the geometry, and this is not a Feynman diagram, but we can still think about this representation as expanding the integrand in terms of some objects, some building blocks. So this is how we will think about it also later. Now, let me give you some examples. So for L equals 1 and 2, these are the canonical forms. For L equals 1, it is just one loop. So the canonical form is the integrand for just the box integral, which is how this looks like in the momentum twistor space. We will then use some notation because these denominators will repeat all the time for each of the loops. So we can just denote them as d1 of the given loop. And using that, we can also very simply write the integrand for the two-loop negative geometry. There is only one. There are two dots, so we can only connect them on a single link. And even in that case, the form is very simple, but already has some non-trivial numerator, which depends on both of the loops A, B, and C, D, which we will denote as N2. And the denominator has two copies of the poles for each of the loops, but has also this 4 bracket coming from A, B, and C, D for two of the loops, the 4x4 determinant, which originates from this quadratic inequality. Now, there is a fascinating property that if we take the negative geometries, which represent a tree graph, so doesn't have any closed cycle, then the canonical form totally factorizes. So the denominator we can just write again. It's the product of these D's for each of the loop, and then all the ABI, ABJ for each of the link. And the numerator is just a product of the two loop numerators that we had here for each of the link. So there is a total factorization of the numerator in terms of these simpler blocks. And we can actually derive it from physics, from some sequence of cuts, and this is the only thing it can be. But if I just write down the inequalities for such a object, I don't know how to derive this canonical form. The inequalities still kind of look complicated, and we would have to do a triangulation, and which is possible, but it's not obvious why everything then simplifies and shrinks into this product. So there is already a question here, how to get this thing directly from first principles, but we can use some hybrid of physics, intuition, and geometry to get this form and then check that it's correct. Now, this will actually, the fact that all these tree graphs have such a simple form, and we will see an imprint also in the integrated result later, this motivates us to do a hierarchy of all graphs and divide the sum into pieces which have the fixed number of internal cycles. So this is an example at 4 loops with 4 dots. We have two different types of tree graphs. Then we have two different graphs, the one with one closed cycle, and then we have one graph with 2 cycles and one graph with 3 cycles. Note that these are still all contributions to the for loop integrand, so it's the same loop order. It's just that the geometry becomes more complicated if we have more links, and this is related to the number of the internal cycles. And the canonical forms for all of the tree graphs are very simple. They are just given by this simple factorization formula. The canonical forms for the negative geometries with cycles have more complicated forms. For one cycle graphs, we actually solved this problem exactly few years ago, and there are some details about it. We still don't know how to kind of derive it from triangulation and mathematics, but we use some ansatz for the numerator and then fix the numerator, imposing conditions where the numerator should vanish, and this completely fixed the numerator. So the one cycle problem is solved, and for the 2 cycle and 3 cycle problem, something we will need for the case we will be interested in here in more details, L equals 4, the for loop. Then we also solve this problem, but we don't have a general method. There seems to be some sort of decomposition that if you have, if you would like to calculate the canonical form for this geometry, you would like to further decompose it into kind of you would consider this object as being a tree, so you can just write the numerator as a product of the 2 loop numerators. Then you consider that there is involved one irreducible cycle, and then dress it with the remaining 2 loop numerators. And then similar thing for the other decompositions, and then the final one would be kind of a really new thing, irreducible 2 cycle object, and this numerator will be extremely constrained. So anyway, so this is just some method that we use to evaluate the forms, but in a sense this looks a little bit like Feynman rules on the space of loops, which of course doesn't make any sense. The loops cannot be represent the fields and so on, but there is some sort of rules how to build the more complicated forms from building blocks of a simpler forms. However, these objects, this is really about constructing the numerator, because if we divide it by denominator, these individual pieces are not logarithmic. The form is not logarithmic, only the sum is logarithmic. All the possible double poles from the denominator cancel. Okay, so this is what I want to say about the integrand. We got some data, so the all three forms with no cycles are trivial and known, or the 1 cycle forms are already non-trivial but still known, doable. For higher cycles, there is some method, but we don't know how it works in general. But we solved the problem completely for L equals 4. When we have 4 loops, so 4 dots, we evaluated all these forms because we will actually want to integrate them. So that was also the motivation for that. Okay, so now we get to the part about the finite function. How do we integrate these forms, and what function do we get? Now, we have this amplitude logarithm represented by the canonical form on these negative geometries, some of them. If we integrate again on this over this Minkowski counter for all of the loops, we do get an IR divergence. But as we saw before, it's a very mild divergence. In dimensional regularization, it would only diverge as 1 over epsilon squared. However, we don't want to get anything divergent. We don't know how to regulate these integrands staying in 4 dimensions. There are some methods we proposed also earlier with Jake, and there is also when we kind of went a little bit off shell with the momenta and saw how it looks like in the momentum twister space, and it also regulated. There is also a way to go on the Coulomb branch of the amplitude, but we don't want to do any of that here. We would like to still stay IR finite. So what should we do? Well, as it turns out, the only thing that is needed is not to integrate over all of the loops. If you take the integrand for the logarithm of the amplitude for L loops and integrate everything out except the last one, the object is still finite. Only the last integration renders the IR divergence, and then it's controlled by this BDS ansatz and so on. So we would like to stop here. We would like to stop at the very last step before integrating over the last loop momenta. Now, what is this function? So this function will have transcendentality weight 2 times L minus 1. If we integrate the last one, it would be 2L, but it will be divergent. We don't want that. So it's 2 times L minus 1. And for 4-point, it will only depend on a single cross ratio. So it will be kind of the simplest possible transcendental function that we get from amplitudes, only depends on a single cross ratio. If we consider a remainder function or ratio function, which only start at 6 point in n equals 4 superangles, they will already depend on 3 cross ratios. So from that point of view, this is simpler, only depends on a single cross ratio. But still, it's an interesting transcendental function of only a single variable. Okay, and so from that point of view, it's the simplest amplitude. This kinematical variable we call Z is a ratio of these 4 brackets. The AB is the last loop we didn't integrate over, so we basically treat it as the external data, not the loop data here, because we don't integrate over it. And this is the only cross ratio you can write given the dual conformal symmetry. Now, this object we can evaluate at each loop order. And again, if we want to formally define the full non-perturbative object, we can just dress it with the coupling constant with the appropriate power of G and resum L from 0 to infinity. The perturbation series is convergent for planar n equals 4. So this would be a convergent sum. It's IR finite, so this is just some function of G and Z. The sum has a finite radius of convergence. Now, we would like also to get to this gamma cusp, which is a leading IR divergence of this object, not this one. So that seems a little bit unfortunate because we worked so hard not to introduce any IR divergence, and then we eventually are interested in the coefficient of IR divergence. Fortunately, there is a formula how to extract the gamma cusp from this f function without introducing any regulator. You just do certain integral over, you have to get rid of the z on the circle of this z variable, and you get not directly the gamma cusp, but some simple differential equation for the gamma cusp. So there is a way how to extract gamma cusp from the f function without actually making it divergent and reading off the leading IR divergence, which we will use later too. Okay, actually this object has other interpretation, not just in terms of amplitudes, but also in terms of Wilson loops. There is a duality between amplitudes and Wilson loops, where null expectation values of null polygonal Wilson loops are dual to scattering amplitudes in planar n equals 4 superangles. And this f function here we are interested in also has the Wilson loop analog as a ratio of 2 Wilson loops, one with a Lagrangian insertion, this is this object, divided by the Wilson loop without Lagrangian insertion. And here it's also clear that in this ratio, the divergences cancel. At the level of Wilson loop, these are UV divergences, not IR, but they do cancel between these Wilson loops. And the ratio of these Wilson loop is some prefactor, which we would call leading singularity. For 4-point, it is just a 4-point one loop integrand in this AB variable. For higher points, it would be more interesting. And this is multiplied by this f function, which is the function that we just introduced, function with the uniform transcendentality at each loop order. This object was studied already extensively before. There are results at weak coupling up to 3 loops, and there is also a result at strong coupling using a dual ADS picture only at the leading order, which scales like G at the large G. At small g, it's an expansion in G square. So our prescription is following. So the L loop f function, the same f function, is a sum over the connected negative geometries, where now the prescription is integrate over all the black dots, but keep this crossed circle fixed. This is the unintegrated loops. Yeah, so integrate over all of them except one, which is fixed. Because if we integrate over the last one, we get the IR divergent and we reproduce the logarithm of the amplitude. But we would like to exactly stop one step before that. So these are the objects that we will now study. They are integrals of the canonical forms for negative geometries, where we integrate over everything except one of the loops. So here are examples of some results for them. So now the loop orders a little bit shift because the integrand here, for example, is a two-loop integrand, but we only integrate over one of the loops. So this is a one-loop object. And you see that the result is extremely simple. It's some log square z plus pi square. So this is a result. Here there is only one contribution. So this is a result for the one loop f function. At two loops, we already have three different negative geometries we need to integrate. Two of them have no cycles, so they are trees. And they are, again, just some polynomials in logarithms. That's it, and pi squares. And the one which has one cycle, the most complicated negative geometries, has already some trilogs and Li4s. And that's the most complicated piece. So even looking at these results, we can get a sense that not only for the canonical forms, not only for the integrand, but also for these integrated answers, the contributions to these f functions, the trees are simple and objects with cycles are more complicated. Now, in this paper, which should appear very soon, we completed the free loop result. I already mentioned that the free loop result was given in this paper. So we are basically at the level of the full result, we are reproducing it, but they, of course, used very different method. Yeah, they directly evaluated the Feynman diagrams for the Wilson loops. But we reproduce it in terms of the negative geometries, and we will see a very clear kind of hierarchy between contributions. So the tree graphs, there are a number of tree graphs. They are still just products of logs, but we can also write them in terms of harmonic polylogarithms with zero entries. So these are just log. This is log to the 6. This is log to the 4. This is log square. So all are just the products of logs. It's very simple. If we look at one cycle, we see a more complicated harmonic polylogs. Actually, this is not just classical polylogs. We have to go to this more general harmonic polylog space. We can do, there are a number of these one cycle contribute. We can look at one, we can look at the other. But maybe to see some pattern, we would like to look at the symbol rather than the functions directly. And if we look at the symbol and compare the symbol for one cycle and two cycle, then we will easily see that there is a more complicated symbol present in the two cycle than in one cycle. And we can actually trace it now back to the properties of HPL. And the property is the depth of the HPL function. So higher cycles have bigger depth. They have less zeros as the arguments of the harmonic polylogs. So the cycle expansion seem to coincide with the depth expansion of the polylogarithmic functions that appear. If we have just the tree, then we have only the zero arguments. If we look at one cycle, the depth would grow by 2. If you look at the two cycle, and this is also encoded in the symbol, the depth would grow to 4. And in the symbol, this is why I would have to go more into the details. It's about the number of the different symbol entries present. The only two symbol entries which are allowed are Z and 1 plus Z. and the number of these 1 plus z kind of control the depth of the polylogarithm. So the 2-cycle object has the maximal number of 1 plus z. And actually the 2-cycle and 3-cycle objects already have both saturate the maximal depth. Now, so this is for the full 3-loop result. Now, at 4 loops and higher, there is just the integration technology doesn't exist to do these integrals and perform that. So the only cases where which we can integrate are the ones which satisfy differential equations. And we have one very convenient differential equation on these negative geometries, which take any negative geometry with like an extra lollipop, and applying some Laplace operator, the right-hand side just removes one edge. So for example, this negative geometry, applying the Laplace operator in this variable z, we get this simpler negative geometry. And we can just solve this differential equation. And then we can basically, with that, we can solve everything. So anything which has this structure, and we already know the right-hand side, we can solve the left-hand side, which is inside this Laplace. We can kind of add this extra edge. So for example, we solve this 4-loop negative geometry and arbitrary L loop, despite, as I said, the integration technology is not there to evaluate the general 3-loop object of this type, or 4-loop object of this type of higher loops. Now, one important thing here, and that was also the motivation to do that, is to look at the gamma cusp contribution of the individual negative geometries. And the first interesting case is really at 4 loops, not at 3 loops, when we can do everything just using more brutal methods. But at 4 loops, if we calculate the gamma cusp contribution of this object, in other words, if we integrate it over AB, then this would be a coefficient of the 1 over epsilon square divergence of this integral. We start to see the presence of the multiple zeta values. And this didn't happen at 3-loop because there was just any multiple zeta we would be still able to write it in some single zeta values at this low loop order. But at this loop order, we already have a presence of zeta phi 3, which is the first multiple zeta value, which cannot be written in terms of the single zeta values. And some simple analysis suggests that if we go to higher loops, we get the zeta values of kind of bigger and bigger depth. But they all cancel in the Wilson loop. So there is a conspiracy between this diagram and other diagrams such that they all cancel in the end. So anyway, so this is perhaps this is another sign of integrability, the fact that only the single zeta values are present. And I think it's an important question to see how this actually happens. Yeah. And this is totally hidden here term by term in this expansion, and we strongly suspect this is also true for Feynman diagrams, but we just don't have any data for these higher loop objects for the Wilson loops going to 4, 5, 6 loops. But I think that from that point of view, these negative geometries are as Feynman diagrams. They would break the single zeta value condition term by term. And there is some conspiracy for the amplitude that everything is just single zeta value in the end. Okay, now I will just quickly go over some older result of tree resummation. There is, of course, once we control certain objects to all loops, we would like to resum them and just to see what happens. And this is also motivated by extremely nice paper by David Broadhurst and Davidice from 2010 when they resummed the ladder integrals. And we would like to do it also with these negative geometries. And we have actually the simple set of negative geometries that we can control to all loop orders, and we would like to resum them. Now, for this ladder resummation, there was a very nice observation that if you go to strong coupling, the result is exponentially suppressed. So we would like to see what happens with these negative geometries, because we know that the object that we are actually constructing, this f function, should be linear in G at strong coupling. So can we get, if we resum all contributions, can we get a result which is linear? So this is the resummation. There is some formula that we used. Again, it was done using differential equations, using some tricks, which I will not review. But while the full object scales like G, this tree resummation actually misses the leading piece. It's not exponentially suppressed, but scales like O1 at strong coupling and has a 1 over G expansion at strong coupling, but it misses the leading piece. However, if you look at the gamma cusp contribution, so how these objects contribute to the gamma cusp of the amplitude, not just the F function directly, they also, at strong coupling, they actually do scale like G. So the full result, because we know the full result from the BES equation from integrability, at strong coupling is 2G plus some corrections. And here the contributions of these trees is 8 over pi G plus some correction. So a different number, but the same order. So now this brings us to kind of the big question here. Maybe the F function is too complicated and there are just too many moving pieces. But if we just restrict ourselves to looking at the gamma cusp, we should get the leading behavior to be 2G. From the trees, we get 8 over pi, which is like 2.55, but also has this weird 1 over pi number. Now, if we add more and more contributions from 1 cycle, 2 cycle, and 3 cycle, are there just small corrections to this? Or are there just some wild kind of numbers, plus, minus, with different signs? It's not even clear that they stay the same order of G. Yeah, all of them. So that's kind of the question. And we have some indication for that, not for the full resummed result, but we look at how I will be done in 1 minute. How the different contributions, the negative geometries contribute to gamma cusp at fixed loop order. So if we look at 2 loops, we already had these geometries and we wrote the F functions for them. So if we look at the contribution to gamma cusp relative to the full result, the 3 graphs definitely dominate here. It's like 1.09 of the full result, and then we subtract a little bit from the 1 cycle graph to get the full gamma cusp. So it really looks like a low cycle dominance. The 3 dominate here over 1 cycle for the contribution to gamma cusp. Okay, so this is very small data. Now we can look at the 3 loops. This is the result from this newer paper. Again, the full result here we scaled as 1, and these are the relative contributions. So the 3 graphs give like 1.2, and then the 1 cycle, 2 cycle, and 3 cycle subtract. Now, this is still dominant, but here we can see that actually the 2 cycle is numerically bigger than the 1 cycle, and then the 3 cycle is then very small numerically. So this is not perfect. There is still some dominance of trees, but this is more confusing. However, at 3 loops, we have now 2 different structures, the pi to the 6 and zeta 3 square. So we can look at these coefficients A and B independently. And if we look at them, there is now a clear hierarchy. So looking at pi to the 6, more and more cycles, smaller and smaller contribution. And for zeta 3 squared, the same is true. Then it actually starts at 1 cycle, and the higher cycles have lower and lower contribution. So there seems to be a hierarchy in the contribution to gamma cusp, and more cycle graph contribute less. But one needs to do this distinction between the different transcendentality the structures in the result, distinguish between odd and even zeta values. Okay, so this is my last slide. So we discussed these negative geometries as the expansion for the amplituhedron and the logarithm of the amplitude. We focused on 4-point, got some intuition how to build canonical forms, and these cycles, internal cycles, if these graphs were an important guide. We focused on this IR finite function for the amplitude, and then this cycle expansion was related to the depth of the polylog. And for the contribution of gamma cusp, it seemed that the low cycles dominate. So there seems to be at least something behind this expansion in terms of these cycles. But there is this big puzzle with the multiple zeta values presence and how they exactly cancel. Things that I didn't discuss that we have also done, and I reference on the first slide, we have some interesting results for 5-point, something on the Landau analysis, and the leading singularities for the higher point amplitudes in this context. And the intermediate future goals is to generate more data. We need definitely new differential equations to do that. Unless we have a new integration technology, which works for for-loop integrals in total generality, which seems too hard, we need some new differential equations specifically for these negative geometries beyond the ones that I showed. And we would like to understand the MZV cancellation and do more on this resummation. We only did resummations on the trees. Okay, I'm sorry, I'm a little bit over time. Thank you.